Hello, in this video we look at the common gate topology, which is similar to the common base in the BJT. So for the common gate topology, the input signal is given to the source and the output is taken from the drain. Now intuitively, let's look at how this topology operates. Assuming there is a bias voltage, so let's call this the gate voltage, and in this case the signal coming in becomes the source voltage, but we know that the current ID is controlled by the VGS. So assuming the gate voltage is at a particular potential, say 1 volt, and there is an increase in the input voltage. So let's just take something like 0.1 volt here. Then in that case, the increase in the input voltage from 0 to 0.1 would reduce the VGS to 0.9. So you have the VGS at a particular potential VGS, then the source voltage is raised. So before the source voltage came in as the input signal, the VGS, which is the difference between the gate and the source, was 1.0. Now when the source voltage is raised by the signal, then it means the VGS will now be reduced to 0.9. depending on the value of the input voltage that went into the source. So clearly we see that an increase in the input signal would mean the VGS would reduce. And if the VGS reduces, then what happens to the current? The current would also reduce. If the current reduces, then the drop across this voltage would reduce. And if the drop across that voltage reduces, we know that V out is equal to VDD minus the drop across that resistance. So if this drop is reducing, then V out would increase. So going back, we see that an increase in the input signal would cause an increase in the output signal. Unlike the common source stage where the input signal increasing and the output signal was reducing, this is the other way around. So the gain in this common gate stage becomes AV is equal to minus GM. Sorry, no minus. So minus is for the common source stage, VD. We are also going to prove this using the small signal model. So we just draw the small signal model this way. Our gate is grounded. Then we have large input impedance between the gate and the source. And our signal is connected to the source. So this is our input V in. So you have VC or VGS, which is controlling the current flowing through the drain. So this becomes our RD and our output voltage V out. So this current is related in this form: the transconductance of the device times VGS. So VGS could be called V1 or whatever voltage. The most important thing is that is this voltage that is controlling the current that comes in here. So what we want to do is we want to find a relationship between V out and V in this ratio form. We will try and take the Kirchhoff's current law or Kirchhoff's at this node, KCL at this node. And when we do that, we can see that V out over RD is the current flowing this way. It should exactly be the same as the current flowing this way, which is equal to GM VGS. So now what we want to do is find VGS in terms of Vin, so that this whole expression would have Vin and Vout in the same equation. Coming here, if we complete the node, we have voltage VGS right here, which is controlling the current through this node. Then our input signal also comes in here. So in completing the node, when we write the Kirchhoff voltage law, Kirchhoff voltage loop we apply Kirchhoff voltage law in this loop, we know that the input voltage would also be grounded somewhere. So indirectly, the end is tied together, and this completes one voltage loop. In the loop, we see VGS plus Vin should be equal to 0. As I said in the earlier video, if you draw your loop and the loop enters the voltage source at the positive terminal, give it a positive value. So the loop also enters Vin at the positive terminal, give it a positive value, and equate everything to 0. Clearly, we see Vin is equal to the negative of VGS, or VGS is also equal to the negative of Vin. Then I can replace VGS here with Vin. Okay. Okay. So something is not right here. So over here in our Kirchhoff law, so we made a mistake here. So what we are doing is that so sorry about that. So taking the Kirchhoff current law at this node, the voltage or the current leaving the loop should all sum up to 0. So we have GM VGS leaving the loop plus Vout over RD also leaving the loop, and they should sum up to 0. So when you send this to the other side, rather they are not equal, but one is the negative of the other one. So this should be the negative of that one. Now we put V in here, which is also negative. So we already have negative here, and we have negative V in, as we explained here earlier on, to replace VGS. Then our gain would now be Vout over Vin, dividing here by Vin and dividing this side also by Vin. Then we have these two negatives cancelling out. Then we can multiply both sides by RD. So times RD times RD. What we do have here is GM RD, which confirms that the gain in this situation, the input and the output are not 180 degrees out of phase as we had for the common source stage. Okay, now we want to take a look at the input and the output impedances for the common gate stage. So clearly, if we want to compute the input impedance, we need to set the output to 0. So the output voltage Vout is set to 0. Then what we have is we place at the input a test voltage source Vx. Then we measure the current that comes out from the test voltage source, which we are calling Ix. So the ratio of Vx to Ix should be equal to the input impedance. Now we try to do that mathematically. Once again, we try to eliminate V1 from our equation, because clearly we can see that the current entering this node and the current also entering this node, the two currents are entering the node, so they should add up to 0. All the currents entering a node or all the current leaving a node should add up to 0. So that means that Ix plus Gm V1 should be equal to 0. Now once again, we want to find relationship between V1 and Vx, because we want, at the end, we want the ratio between Vx and Ix, not V1. So V1 being the controlling voltage, as we did earlier on, V1 is going to be the negative of Vx. So all I will do is I will write Ix plus Gm negative Vx. Okay, it should be equal to 0. Then I move Gm Vx to this side. So all I need to do now is to find Ix, Vx over Ix, which will be equal to, so Vx over Ix should be equal to 1 over Gm. So that tells us that the input impedance seen, or the impedance seen at the source, which is the input impedance, is 1 over Gm, which has been proved using the small signal analysis. For the output impedance, we have, just as we did for the common emitter stage or the common source stage, because in finding the output impedance, we connect our test voltage source, this time the Vx, to the output terminal, and we set the input terminal to 0. So once the input terminal has been set to 0, this is not different from the common source stage, because the common source stage, the input was given to the gate, but when you are finding the output impedance, the input is still set to 0. So in this scenario, it doesn't matter whether the input was given to the gate or the input was given to the source, because either way it will be set to 0. So that tells us that the output impedances should be the same. Now you see Vx has to be 0, V1 has to be 0, then it means this guy too would have to be 0. Then that tells us that if you look at this, Vx over Ix definitely has to be Rd, and that will be the output impedance for the common gate stage. What we notice in the common gate stage is a significant reduction in the input impedance. The common source stage had an input impedance of infinity to low frequency signals. Now we are talking about a new topology that has low input impedance. How is this important? Okay, so we look at what we call the maximum power transfer or maximum power transfer theory. Now it states that for maximum power to be transferred from a source, so if I have maximum power, if I want maximum power to be transferred from a source to a sink, the impedances should match. And this can be proven. So if the impedance seen here at the output of this stage is equal to the impedance at the input of this stage, then I can get maximum transfer of power. Now, if we wanted to use the common source stage, which has an input impedance of infinity, then the maximum power transfer would mean that the output impedance of whatever stage is coming should also be infinity. So typical example is in antenna applications. An antenna usually has an impedance something 50 ohms or 100 ohms. So let's assume 50 ohms. Then we want to give our signal to an amplifier to amplify the signal for us. Knowing very well that the output impedance of the antenna is 50 ohms, for maximum power to be transferred from the antenna to the amplifier, what we do require is 50 ohms here. And if we are using the common base stage, we could easily do that by making sure that 1 over Gm is equal to 50. So we could design our circuit such that the 1 over Gm is equal to 50 ohms easily. Taking the formula for gain 2ID over the formula for Gm over Vg minus Vth. Then we could design our circuit so that this value of Gm, 1 over that, should be equal to 50. And we could work out the required values that we need to bias our signal to get the required input impedance. So that is how useful the common gate stage could be. So in the next video, we will look at the common source stage. Before we end, we also have to take a look at one important aspect of the common gate stage. Now, drawing the common gate stage like this, okay, and this is the bias voltage. We have ID. When we connect our signal, assuming it's a microphone, then how do we have our ID going through the signal? That's one thing we should look at. Assuming you have a microphone would work. Assuming for some reason you wanted to, or a situation where you had a capacitor between your microphone and your source or your signal, your amplifier. In that case, if you had the signal ID flowing through, there will be no path for the DC signal to go to the ground. So you will need to create another path for the DC signal. Now, if you decided to short circuit this, then there's a path for the DC signal to go to the ground. But when the microphone signal is coming, or the signal that you want to amplify is coming in, then the signal would also go to the ground rather than going to the transistor. So to overcome this, you need to create a path. There are two ways of doing that. Either you place a resistor to create a path for the bias, or you could also use a current source which would properly bias the amplifier. And this is very crucial, especially in antenna applications. In antenna applications, the antenna itself creates a form of so the antenna usually looks like this. sorry, something like this. Okay, and this creates some form of capacitance between the signal coming from the amplifier this way before connecting it to the so without this part of the circuit, then there will be no path for the bias ID current to flow to the ground. Or you could also use a current source which would bias the transistor. Then finally, we look at another scenario. Assuming we're using a microphone as our input signal, and a finite microphone, which is not an ideal microphone, would have some internal resistance. So this is our internal resistance. So R internal before our signal comes in. And we take our output from here. So looking at this carefully, we could see that this resembles some form of degeneration created by the internal resistance of the microphone. So the question for today is, how does this affect the gain? Or moreover, does it even affect the gain in any way? Okay, so until then, see you next time. Bye bye.